Okay, in section 2 we're going to talk about function, arithmetic, and composition, and then manipulation of graphs in the sense of rigid motions and stretches and skews of the graphs of functions. So let's first talk about the functional arithmetic. So if I have a function f of x and I've got a function g of x, I can add them together, I could subtract them, I could multiply them, or I could divide them, right? We can do more than that. You can take the entire function and you can put it in an exponent or such things like that. But mostly these are all different types of compositions of functions in some sense, right? Maybe I had a function of two variables, x and y, and I've got x plus y as the output of that function. Well, if I take a function f and I take a function g and I take a function h and I put them into this f function, which adds things together, that's composition of two functions, which gives me addition of those two functions. Okay, so composition is putting one function inside of another, right? So you do the input-output thing for one of the functions. Whatever output you got, you put it into the input for the next function, and that's function composition. So I've got f of g of x, right? I've got an input. I get the output for g, and I use that as the input for f. So in some sense, graphically, I start with x, I hit it with g and I get g of x. I hit it with f and I get f of g of x. And that's function composition. You take an initial input, you do something to it, whatever the result of that is, you do something else to it, whatever the result of that is, you do something else to it, right? I can keep continuing this on if I wanted to. I could hit f of g of x with h, and I could get h of f of g of x. Right? And this composition can continue as long as we want. I can have functions of multiple variables that I do this composition with, but composition is putting one function inside of another. And this is kind of an important thing with calculus because there's this idea of the chain rule where I can find derivatives of compositions of functions, and being able to simplify a complex function into different parts where you've got like an inside function and an outside function in this composition, and then being able to do or analyze each of those pieces to analyze the whole function itself makes things a lot easier and is kind of a powerful concept. So let's say we're going to decompose this function here. I've got this function that I'm going to call let's call it h of x. It's going to be x plus 1 squared, and it's going to be minus the square root of x plus 1 minus 1 over x plus 1. And I want to decompose this into two different functions. Well, I see a lot of x plus 1's floating around, so maybe that should be my inside function. That's the function that I put into another function and think of it as the input. So we're going to decompose this as f of g of x. Right? So my inside function g of x is going to be the thing that shows up all over the place. So we're going to let g of x equal x plus 1. Okay, so this x plus 1, it shows up here, and it shows up here. Okay, so we're going to rewrite h. We're going to write h equals g squared minus the square root of g minus 1 over g, right? Because that's what h does. It takes this g stuff, it squares it, it subtracts the square root of g minus that 1 over g again. Okay, and so that's going to be my outside function. My outside function, f of g, is going to be g squared minus the square root of g minus 1 over g. Okay, if I do that, then together what these things do is they give me that f of g of x is g of x squared minus the square root of g of x minus 1 over g of x, which when I look at g of x is 1 plus x. This is, or x plus 1, however you want to read it, squared minus the square root of the g, x plus 1 again, minus 1 over x plus 1, which is h of x. So I've decomposed h of x as an inside-outside function. We've got it written as a composite function. That's going to be sort of a powerful thing for us. Let's look at how some of this stuff works with the graphs of these functions. Okay, so we might recall that, let's say if I have f of x, then f of x plus c. If I call this thing g of x, the graph of this has each of the outputs of f plus a c value added to them. So this takes this graph of f of x, if this is the graph of f of x, maybe I've got this thing, then if I add c to it, it shifts it up, right? It goes up. Takes this, shifts it up by c. If I do a minus sign there, this is down by c. Okay, so up and down is pretty easy. You just add some constant to the outside of the function. Left and right is also pretty easy. If I take f of x and I transform it into f of x plus c on the inside, this is a shift left in the graph. So let's look at, say, f of x. We'll do a specific example with this one, x squared, and then I look at f of x plus 1. This is x plus 1 squared. Well, this is my parabola with the vertex at the origin. This is a parabola, but its root is at -1, right? So the vertex has been shifted to the left 1. I've made each of the inputs bigger by 1, which means everything happens sooner, right? This says look forward to one spot and do it now, right? Look one spot ahead and do that input now instead of the input of x. So it's bringing back everything. It's looking ahead and bringing back that function to where you're standing now. Similarly, f of x minus c, this is a shift right. So it says, wherever you are now, look backwards in time and do what happened back there now instead. So it sort of delays things from happening. Where adding a value sort of makes things happen faster. Subtracting a value makes things happen slower. Same thing with multiplying values, right? So if I take c times f of x, this makes everything c times as big. Each of these outputs is now c times as big. So if it was at 1, it's now at c. If it was 2, it was at 2c. So it stretches things up vertically by a factor of c. If C is smaller than 1, that stretch becomes a compression. If I multiply on the inside, this says all of these inputs happen C times as fast. So if C is big, everything happening 50 times faster means everything's compressed together horizontally, right? So this is a shrink horizontally by a factor of C. So if C was 50, everything would be really, really close together, and like if I do, say, a basic trig function, say f of x equals the sine of x, right? Then f of, let's go 3x, everything's going to be 3 times as fast. So that means in the same amount of time that it took me to do one cycle here, from here, up, down, up, I have to be able to do 3 cycles. So I go 1, 2, 3. 3 times as fast. 3 times as fast this way too, right? Okay. Did I get 3 there? 1. No. Yeah. Okay. And then finally flips negative f of x. This flips vertically. F of minus x flips horizontally. Right. Vertically happens because it happens to the output, right? Up here, the C is multiplied to the output, so it's a vertical thing. We did adding stuff to the output is a vertical shift up or down, right? If it happens inside the parentheses, it's an input effect. It affects the input, so that's going to affect the x-axis. It's going to be a horizontal thing, right? Multiplying inside here, I had a horizontal effect because it affects the inputs. Minus sign inside is going to be a horizontal flip because it affects the inputs. Alright, that's 1.2.